So Mary, what is a powder? How would you define a powder?
Well, I think a lot of times, and you've mentioned it before, most people know what a powder is in theory, because we find them in so many places. When we were discussing this before, market mattered. So when we're talking about in the category of powders, we could have spices, ingredients. The pharmaceutical industry also uses it for excipients and APIs, and they serve a lot of different functions. Basically, a powder is like a small granular product, right? We found a good definition in Ho, Tron, and Bandari from 2017. And just to paraphrase that, it talks about structure as being the main definition of a powder. So amorphous, crystalline, combinations of those two together, depending on and how those interact, and how the particle size will affect the functionality, the application, and the production of the powder. So I think those are really kind of sum up why powders are such a huge market and why they're so difficult, because they span so many different markets and function groups.
And we had spent some time before. We've done a previous webinar on powders, and we dove a little deeper into looking at amorphous and crystalline. And I think basically from a molecular structure, there are some key differences. A crystalline structure will have a repeating structure that's well defined. That's something you can see on a molecular level, and then even visually, you can generally see these differences in powders. And I believe we have some figures for that. And then last time we did talk about mixing these powders and looking at some of the combined effects. So if you are interested in looking more at that, you can look back at our previous webinar. We also talked a little bit about particle size, and I want to hit on that a little bit more. How does particle size affect some of the characteristics of powders?
Yeah, particle size really is a major impact for characteristics in powders and why they can be so difficult. When you have small particle sizes, then you can get a bridging between those particles that you don't anticipate, and then you can start getting them sticky and have agglomeration and things like that. So there are a few things besides just general particle size. You can have particle shape is also a factor too. When you mix, there's been some research too. When you mix crystalline powders together, you will have them what we call deliquesce, which is basically go from a solid to a liquid state earlier than you would anticipate either of the individual powders doing. And the reason is, I think it's because of the having different sizes of particles. Whenever you get these places of contact, you can start having bridging and problems. So crystalline powders can be particularly tricky because, as you said, they have a very ordered structure, and that means that the moisture only adheses essentially to the outside of that structure. It's only a surface interaction, as opposed to with an amorphous, there's a lot of crevices and irregular shapes and sizes, and water can more easily bind with the amorphous. So that does make them functionally different, but it also impacts when you have to use them as a formulator, right? How are they going to go in a production facility?
And last time we talked, we looked at the 5 stages of caking. There's multiple steps to getting to agglomeration and then eventually to liquefaction. And we don't necessarily need to go through them today, but I do want to point out that caking and clumping can start to occur at an early stage. And, one way to control this is by looking at maybe the moisture and the water activity of these powders. And so I thought, we do this in most of our webinars, but it's always really helpful to define what moisture content is and water activity, and talk about how we can use these things together to think about physical changes and chemical and microbial stability. So let's start by looking at moisture content and water activity. I know you have a pretty good graphic for this and a good definition. How do you differentiate these two different measurements?
For some of the people we speak to, water activity is a new concept, and most people are very familiar with moisture content. So I like to separate them and say that there's 2 water measurements that we can make. So there's 2 different ones. There's one where we're looking at the amount of water, which is the moisture content, versus the energy of the water. What is the water able to do? And we do measure those in completely different ways. When we look at moisture content, that's a mass percent, so we're just looking at a weight. When we're looking at water activity, we're actually measuring what we call a vapor pressure. So that's similar to what the the humidity is coming off of a sample, right? So if you want to kind of look at some of this, our research and some of our other webinars, we talk about water activity. It might be helpful to consider what we're also saying is basically an equilibrated humidity that the sample is putting off. And that might help people understand these two things a little bit better. And also how some external and ambient conditions can affect their product, which I think is also something to note and to monitor as well.
And I think it's a good point. I still see it misdefined pretty often, that water activity is sometimes defined as water availability, and that's not exactly the right way. I mean, water activity is a thermodynamic principle. It really is the energy of that water. And it's important to know because the energy of that water can be used for a chemical reaction or texture change or something else. So I think it's really good to really hone in on that point. We are looking at the energy of the water with water activity. And moisture content, if you only look at moisture content, we have clients that come to us all the time who have a really good record of moisture content, but they have a really hard time getting a precise measurement. And because they can't be precise with moisture content, it's really hard to connect some of the problems they're dealing with to moisture content. So moisture content alone isn't going to give you all the information you need, especially for powders. So by combining water activity and moisture content, we can look at the isotherm. And this is something that we always talk a lot about, but it's because it's really a unique way to look at the water in these products and get a complete picture of how the water is behaving in that product. How do you take an isotherm? How do you look at that shape and correlate it to different characteristics of a powder?
Yeah, you can look at, some of the ways that we use isotherms is to define a critical point, a critical water activity, where we're going to start seeing texture changes and other changes within the structure of the product. Basically, at what point does it start to change and take on a lot more moisture, right? And generally, if we're talking about a powder, that is the point where you're going to start seeing caking and clumping. If we have some kind of other product like a snack, you can start getting soft. And so those are really critical points to find out. We can also look at the slope or the shape of the isotherm itself too, and be able to identify the structure, like we talked about amorphous versus crystalline. We can look at that. We can also, by exposing these samples to humid air and basically in real time see how they behave, we can get a lot of really great information about that product that's can be really useful for a client.